Hello everyone, my name is Anousheh Gholami, and I'm going to talk about drone-assisted communications for remote areas and disaster relief. Sorry. I'm working with Dr. John Barras. So I would like to ask you to think about this picture. So these pictures are not actually taking pictures from a base station or from the sky. This picture was actually taken after Hurricane Maria in Puerto Rico in September 2017. And they are actually looking skyward in search for some signal to communicate maybe to their family members or whatever. So according to US Federal Communication Commission, a week after this hurricane, about 90% of the cell size of the island was totally out of commission. So the main question is that can we use drones as flying base stations to provide service in scenarios like this as a disaster relief or for even remote areas? As a background, so recent advances in UAV technologies have made drones more accessible and also affordable. So historically, they were mainly used in military applications. But, for example, Amazon is looking into using drones for cargo transport, in wildlife conservation, as we saw in previous talks. So there are some applications that are more into the commercial applications for agriculture, for traffic monitoring, for emergency search and rescue, and for communication relaying. So basically, if you can just equip a drone with radio access technologies, then it can actually act as a flying base station. And the main advantages of using this scheme is that, first of all, because drones are operating at some height from the ground, so in terms of communications, their communication to the ground is expected to have better performance because of the existence of the line of sight communication. Moreover, they are actually more cost and power efficient compared to other alternative solutions such as satellite communication, which is very, very expensive. Of course, they can be mobile because you can actually easily just move them as the traffic pattern changes or as the topology of the ground network changes. So this is another important advantage. And of course, their deployment is much, much faster than alternative solutions in disaster relief scenarios. So for communications relaying, as you can see in the picture, there are three main realistic applications nowadays. First of all is for disaster relief. Second, for high demand area. Assume that you have like an event with thousands of people all want to communicate like simultaneously, so in stadiums or in concerts, and the cellular network cannot respond to this high demand. So the idea is to add drones to just offload some of the load on the cellular base station. And of course, for remote areas where it's not cost effective to use terrestrial communication, so drones can also be helpful for broadband communication. So the main objective of this project is to deployment of multiple UAVs in a multi-wireless attack network to support the traffic demand of the ground network that are some disconnected users and are not supported by any terrestrial infrastructure. And the main challenges with this problem is first, because drones are of course not cheap, so we want to use as less as possible in terms of the number of resources we need, number of UAVs, and also the power consumption, because drones have power constraints. So they need to go back to some place to be charged and then again be in operation. Of course, we have a scarce spectrum, and we have interference management problem. And we also want to consider both the access link connectivity and the backhaul link connectivity. So most of the existing solutions in these scenarios are only considering the access link connectivity, meaning the link between the drone and the ground. Nothing after that. And of course, they are not considering the traffic demand of the ground network into consideration for UAV placement. So as you can see in the picture, so the main idea is that you have a ground network consisting of a number of devices. They can communicate to each other, and because there is no base station available, they want to talk to the drone, and then the drone is going to relay the traffic demand to other users or to a gateway. So our proposed framework is mainly decomposing this problem into three phases. In the first phase, we want to cluster the ground network, and each cluster is supported by at least one drone. In the second phase, we want to use minimum number of UAVs to support this cluster, and we want to actually place the UAVs because it's important to where you place the UAV to operate. And at the last phase, we want to use an energy-aware routing because, as I mentioned, the drones have power constraints. So we want to have an energy-aware routing. So in the first phase, as I mentioned, we have a ground network clustering problem. So we actually use K-means algorithm, which is very simple and converges pretty fast. And then we want to, for initialization, we use density box-based initialization, which considers the density of the ground network. In the second phase, we have UAV placement. So for UAV placement, we consider two problems, capacity problem and then connectivity problem. For capacity problem, as I mentioned, we want to use a number of UAVs that we're sure that are actually supporting the traffic demand of the ground network. So one basic idea could be just using the centroids of the clusters we found in the first phase as some initial position for the drones. So that would work. And then if you add these UAVs and see that the network between the UAVs is actually disconnected because they can be far away from each other. So we are adding, in the second level, we are adding more UAVs to make sure that the resulting network is connected because we don't have any terrestrial or satellite communication available. So this problem, backhaul connectivity problem, can be formulated as an optimization problem, as you can see. So this is actually an extension of the discovering problem, which is NP hard, very hard to for finding the solution. So we adopt a heuristic algorithm, which is pretty fast, based on deterministic annealing, to find suboptimal solution for the UAV placement. And finally, we have an energy-aware routing. So in order to extend the operation of the UAVs, so we want to have an energy-aware routing. And for each source destination pair on the ground, we find a number of paths, and then for each path, we define a cost function that is basically the power required for that path to communicate end-to-end. So then the objective is to minimize this power consumption, the power required for communication, and also to minimize the unsupported traffic. So this problem is actually a multi-objective problem, can be formulated as an optimization problem, which is a mixed integer linear program. The integer variable comes from either choosing a specific path, end-to-end path or not. And then we have a variable, continuous variable for percentage of the traffic that is actually non-supported. And we have a flow split variable, continuous variable. So this optimization problem is a mixed integer linear program. As I mentioned, it can be solved by available solvers like Cplist that are used. And in terms of performance evaluation, so this is one example to see how the UAVs, our algorithm places the UAVs. In this example, we have a network of 40 nodes, 40 ground nodes, and they are in 3 clusters. So on the right figure, you see the existing solutions that only consider like the connectivity. So on the right figure, UAVs are added to the network. 2 UAVs are added. Actually, here 2 UAVs are enough to connect these disconnected clusters. So this actually ignores the density of the nodes or the capacity demands of the nodes. But on the left figure, we see that the configuration, the placement, and the number of UVs actually changes accordingly because we are considering the demand and the density. This is actually another example for the case of 170 nodes, and we see again our solution considers the density and also the capacity, and the number of UAVs and the placement changes accordingly. And in the last picture, I have the comparison. On the left figure, we have the comparison between the connectivity-based solution and our proposed solution. So in the solution that you only consider the connectivity, the percentage of unsupported traffic can go, for this example, up to 40%. And on the right figure, we have the effect of energy-aware routing. So when you have the objective of energy-aware routing, you may lose some of the traffic demand because there's some trade-off between supporting the ground network or considering also the energy consumption. So this is actually showing the trade-off between these two. So as a conclusion, in this work, we considered placement, UAV placement, and traffic routing for a ground network that is not supported by any infrastructure. That is the case in disaster relief scenarios or in remote areas. And we consider both front-haul and backhaul connectivity, while most of the existing solutions only consider the front-haul connectivity. And we have also some energy-aware routing algorithm to mainly extend the operating time of the UAVs because they have power constraints. And the main question is that we actually want to exploit the mobility, the capability of the UAVs. So assume that the ground network topology is dynamic and we have dynamic traffic patterns, so we need to move UAVs and going from one placement to the next placement. Thank you very much.
Questions?
How are you identifying the traffic density? Like, if there is no connection that you're finding on your phone in case of disaster relief, how are you finding the traffic density?
Yeah, that's a good question. So in the case of, usually what people do is doing some estimation. So assume that you have first searching, like a scheme that you spot the people who need communication on the ground. So that's another problem. But actually, you need to do some surveillance at the beginning to see where the people are placed who need communication or need help, and then bring UAVs to help for the communication.
This might be based on my lack of understanding of how the cell network works. But I was wondering if, in a situation like where all of the cell towers are down, what do the UAVs communicate with in order to connect to the network, connect the people to the network in the first place?
Yeah, so if I understood your question correctly, so you mean that you have a cellular network and you want to add UAVs to help the cellular network, and then how they communicate to each other?
How do they communicate to the network itself?
Okay, so there are actually different protocols. So there are different actually solution or proposals because this scheme is still ongoing in terms of a unified standard worldwide. But usually you can assume that they can use cellular connectivity, cellular protocol, or they can be connected by Wi-Fi that has short range, or people are talking about millimeter waves. So there are different, proposals, but nothing has been standardized right now. If I answer your question, you can talk maybe offline.
Let's thank the speaker one more time.